On this example, we want to find the x-intercepts of the graph of the function without graphing the function. Our function is f of x equals the square root of x plus 11 minus the square root of x minus 1. And we want to find the x-intercepts of this function. Whenever we're looking for an x-intercept, the x-intercept is where the graph crosses or touches the x-axis. And because it crosses or touches the x-axis, the y part will be 0. And so that's how we find x-intercepts, is by letting y equal 0. Now our equation here is written in function notation, so f of x represents y. So we're going to let f of x equal 0. So we have the equation 0 equals the square root of x plus 11 minus the square root of x minus 1. And this is what we call a radical equation or a root equation. The strategy that we're going to use to solve this type of equation is to isolate the radical and then get rid of the radical. So I'm going to start by adding square root of x on both sides. And I'm adding square root of x so that I have that radical isolated. So now I have this radical, square root of x, isolated on one side of the equation. Once you have it isolated, then you're going to get rid of it. So the way you get rid of a square root is to square. I'm going to square the left, and whatever you do to one side, you have to do the same thing to the other side. So you square the right, and the square root will cancel each other out on the left, so we're just left with x. On the right, it's going to get a little bit messy. We are squaring a binomial, so I'm going to write it twice. Because that's what squaring means. Squaring it means multiply the base 2 times. And then I'm going to multiply it out up here. We have x equals, and we're going to multiply these first two together. Square root of 11 times square root of 11. Excuse me, I misspoke. That's square root of x plus 11 times square root of x plus 11. That's x plus 11. Then I want to multiply the outside 2. That's square root of x plus 11 minus 1. That's minus 1 square root of x plus 11. Then I want to multiply the inside 2. And that's minus 1 square root of x plus 11. And then finally, I want to multiply the last 2. That's negative 1 times negative 1, which is a positive 1. So before I go any further, I want to make sure you understand how we got each one of these parts. So let's pause on this part right here, how we got x plus 11. I'm going to write up here, we're multiplying square root of x plus 11 times square root of x plus 11. And that's equal to the square root. Now when you multiply square roots, you multiply what's underneath them. So that's the square root of x plus 11 squared, and then the square root and the square cancel each other out. So that's how we got x plus 11. Then let me check to make sure that you understand how we got this part. When I multiplied x plus 11 times -1, one of the numbers is in a square root and one is out of the square root. And those don't mix. So like on this one, both of these were inside a square root, so we multiplied them together. But when one's on the inside and one's on the outside, we leave them that way, just like we have it here. So that's how we got that one. All right, so with that cleared up, I'm going to continue. And I'm going to start combining like terms. So I've got a positive 11 and a positive 1 that will combine together. That's x plus 12. And then these two terms, we call these like radicals, sort of like terms. And when we combine those together, we're going to have -2 square root of x plus 11. And so we have, at this point, accomplished getting rid of this radical right here. However, we still have a radical in the problem, so we have to repeat that process over again. We isolate the radical and square it to get rid of it. So I'm going to subtract x on both sides. As 0 equals 12 minus 2 square root of x plus 11. I'm going to subtract 12. So negative 12 equals -2 square root of x plus 11. And then I'm going to divide both sides by -2. Negative 12 divided by -2 is +6. And now I've isolated this radical. Once you isolate it, then you try to get rid of it. So to get rid of this square root, I'm going to square. I'm going to square the left and also square the right. The square root and the square cancel each other out, leaving me with x plus 11 on the right. 6 squared is 36. And then I'm going to subtract 11 on both sides. That gives me x equals 25. Now, it seems like we've got our answer, but there's one more thing that we have to do. And it's because of us doing this step where we square both sides. It's possible that when you square both sides that you get what we call extraneous solutions. These are extra solutions that don't work in the original equation. So what we have to do is we have to check to make sure that we don't have one of those extraneous solutions. So we're going to check our proposed solution of 25. We're going to check that x equals 25 in the original equation. So I'm checking it in this equation right here. So our equation is 0 equals square root of x plus 11 minus square root of x minus 1. I'm going to substitute 25 everywhere I see an x. That's 0 equals 25 plus 11 minus square root of 25 minus 1. Square root of 25 plus 11. 25 plus 11 is 36. Square root of 36 is 6. Square root of 25 is 5. And I have 6 minus 5, which is 1, minus 1, which is 0. So this is a solution to our equation. And so we're going to keep it. And this is our x-intercept. We have an x-intercept of 25, 0. On this example, I want to use the graph to determine the domain and range of the function. We're given a picture of the function, and from this picture, we want to state the domain and range. A very common mistake for finding the domain in a question like this is to take a look at these ordered pairs that are labeled on the picture and list the x's as the domain and list the y's as the range. Now, the reason why that is incorrect is because when we find the domain, we're trying to find all of the x's. And if you list out just these numbers, you're only getting the domain for those individual points. So we're going to use interval notation, and interval notation will allow us to get all of these values instead of just these individual ordered pairs. So we're going to find the domain. And when I'm finding the domain from a graph, I like to use a pencil or a ruler, and I hold that ruler vertically when I'm finding the domain. And I'm holding it vertically because holding it vertically is pointing to your x scale. So I'm going to start from the left and move to the right. And I'm starting on the left because the left is where your x values are lowest. We always write interval notation lowest to highest. So I'm starting on the left, and I'm going to figure out where my domain starts. And I figure that out by when my ruler hits the graph the first time. So right here, my ruler is hitting this point right here. That point has an x value of -9, so that's when my domain will start. If I continue moving to the right, I can see that my ruler is touching the graph. The last time that my ruler touches the graph is at this point right here, which has an x value of 4. So that's where my domain will stop. Now, interval notation uses parentheses when the number is not included in the set, and brackets when the number is included in the set. So you can see that this ordered pair has an open circle, which means that point is not part of the graph, and -9 should not be part of our domain. So we're going to use a parenthesis. However, this point has a closed circle, and the closed circle is part of the graph and is part of the domain. So we're going to use a bracket on the 4. So we have the domain being -9 to 4, not including -9, but including 4. Then we're going to find the range. And with the range, I want to hold my ruler horizontally because that will point to the y scale. And we're going to start at the bottom and move to the top. The bottom has the lower y values, the top has the higher y values. So the first time my ruler hits the graph is at this point, and this point has a y coordinate of -10, so that's when my range will start. Continuing on up, I'm touching the graph, so all of these values are part of the range. The last time my ruler hits the graph is at this point here, which has a y coordinate of 6. So once again, interval notation uses parentheses when the value is not in the set, and brackets when the value is in the set. So because this point has an open circle, that point is not included in the graph, and we should not include it in the range. This point has a closed circle, and it is included in the graph, and we should include it in the range. So just before we wrap this question up, I want to make sure you understand what this interval notation actually means. So with the interval from -9 to 4, this is x values, and we're going to mark -9 on your number line and mark 4 on your number line. We're not including -9, we are including 4, and we're going to shade the values between these. So this interval notation doesn't just represent the two numbers that we've written down, it's all of the numbers between those two. And then when we use the parentheses and the brackets, it tells us whether we're including the endpoints or not. For the second one, this is on our y scale, and we're going to mark -10 and 6 on our number line. -10 is not included, but 6 is, and we shade between. So this interval notation, -10 to 6, is including all of the numbers between -10 and 6, but not -10 and yes to -6 being included. So this is the question in my math lab, so I thought we would just go ahead and type the answer. So what we saw is that our domain started at -9 and went all the way until 4. We're using a parenthesis on the -9 because of this open circle. So I'm using my keyboard to type parenthesis and -9. Then I'll do a comma. And the domain continues until 4. And I'm going to use a bracket because of this being a included circle, a closed circle, and I'm using the keyboard to type the bracket, and we've got that one correct. And for the range, we're looking at the y values, so we start with the lowest y value of -10. And this is an open circle, so that point will not be included. So I'm going to use a parenthesis from my keyboard. That's a -10, comma, and the highest y value here is a 6. This point is closed circle included in the graph, so we're going to use a 6 with the bracket from the keyboard. So for this question, we want to use the graph to determine the domain and range of the function. So we're using the graph to determine that domain and range of the function. And this may be an unusual looking graph to you. It has some features that you may not be familiar with. We've got these dashed lines that are showing up on the picture. And these dashed lines are something that we're going to be learning about in a later chapter, and they are called asymptotes. So let me just explain what's happening on this piece of the graph here. So if we look at this piece of the graph, I'm having a little bit trouble with my whiteboard. If we look at this piece of the graph here, when we have an arrow on the end of our line, it typically means that the graph continues off of what we're viewing, off of the screen. So typically, if that dashed line wasn't there, we would assume that the arrow just keeps going down and to the left, or sorry, not the arrow, the graph keeps going down and to the left and down to the left and down to the left forever and ever and ever. Well, it does do that. It keeps going down and to the left. However, this dashed line that we see means that it stops at that line. It's never going to pass that line. So it does keep getting closer and closer to that dashed line. So it does keep going down to the left, but it never crosses that dashed line that we see there. The same thing is happening on this side over here. So because we have that dashed line, which is called a horizontal asymptote, the line is continuing the pattern to get closer and closer to y equals 3, but it never gets there. It just keeps getting a tiny bit closer and a tiny bit closer. And then over here, we have those vertical dash lines. Those are vertical asymptotes. And the same thing happens. These lines are getting closer and closer to the dashed line, but never reaching it. And the same thing is happening up here as well. So that's a feature that you may not be familiar with. We are going to study it a little bit more later. But with that in mind, let's find the domain and range of this graph. So when I'm looking for domain and range of a graph, I like to use my ruler. And when I'm finding domain, I hold the ruler vertically. And the reason why I hold it vertically is because it allows me to mark off different places along the x-axis, which is important for domain because the definition of domain is all of the x's. So I'm holding this ruler. You might want to use a pencil vertically. And I'm going to go from left to right. And I'm going from left to right because I'm going to use interval notation. And interval notation always goes smallest to largest, left to right. Okay, so when I am looking for the domain, I'm looking for the first time that my ruler hits the graph. So I can use that as my lower bound, my lowest value in the domain, my lowest x value. And then I'm going to look for when this ruler stops hitting the graph as my highest part of the domain. So let's start doing that here. So because of this arrow that we see here, as I said a moment ago, that means that the pattern continues. This graph continues off screen to continue to move down and left, getting closer and closer to that dashed line. And so that indicates to me that the domain is going to start at negative infinity. So as I keep moving to the right, I'm hitting the graph. I continue to hit the graph. And then we reach this dashed line here. So hopefully you remember what I mentioned is that my graph will continue to get closer and closer to that vertical line without ever reaching it. So because it never reaches it, I have a gap in my domain. So my graph does not have an ordered pair with an x value of -2. So that vertical line, that vertical dashed line, is right on -2. And there is no ordered pair on this graph that has an x value of -2. So I'm going to stop my domain at -2, and I'm going to put a parenthesis on -2 because -2 is not part of the graph and it's not part of the domain. However, right after the vertical line, you can see that the graph continues after that vertical dashed line. So my domain starts again. So my domain is going to start back up at -2 and continue until I get to that next vertical line, which is right here at 2. So the same thing happens. This piece of the graph gets closer and closer without ever reaching it. So my domain continues till 2. If I go all along this vertical line, there is no part of the graph. There are no ordered pairs that have an x of 2. So my domain takes a break at 2, but then right after 2, this piece of the graph continues. So from 2 to infinity, I have x values that are part of the graph. So this is my domain. The domain of this graph is from -infinity to -2, union with -2 to 2, union with 2 to infinity. So if we think about this on a number line, we're saying that -2 and +2 are not part of the domain, and every other number on the x-axis is a part of the domain. We found the domain. Now let's find the range. So when we find the range is the set of all y values. We're going to switch our ruler to be held horizontally. Let me erase all my markings here. And I'm holding this ruler horizontally because that's going to mark out different places along my y-axis. And remember, the range are the y's, all of the y's. So I'm going to start at the bottom, that's the lowest y value, and move to the top. So as I look at this, the lowest y value, because of these arrows, meaning the pattern continues, that means that my range will start at -infinity. As I move my ruler up, I'm still touching the graph, and I continue to touch the graph until I get to this spot right here. And this spot has a y value, that ordered pair is 0, 0, has a y value of 0. So my range is going to stop at 0. That point, 0, 0, is part of the graph. It is included in the graph. And 0 will be included in my range. So I'm going to use a bracket on 0 to say that that point is included. We notice that the graph does not touch, the ruler does not touch the graph for this whole section here in the middle. And it's not until we get to this dashed line here that we have some more pieces of the graph. So my range is not going to start again until y equals 3. Now I'm not going to include 3 because this piece of the graph and this piece of the graph are indicating that the line gets closer and closer to a y value of 3 but never reaches it. So 3 is not a point in the range. So we're going to put a parenthesis on the 3. And then as we continue, you can see these arrows at the top. And these pieces of the graph go on forever, and all of the y values are covered. So my range will continue to infinity. So we found the range to be -infinity to 0, 0 included, union with 3 to infinity. So I've got this question that a student sent me, and this is a really, really common question that I get. relating to parentheses and brackets with domain and range, and also increasing and decreasing. So what we're looking at here is 2 questions from homework. And one question gives us this picture here and asks us to find the domain and range. And you can see in the answer we use brackets. And over here in this question, we're given a picture and we're asked to find intervals of increasing, decreasing, and constant. And when you look over here at the answers, parentheses are used. So that's the question. Why are we using brackets in one case and parentheses in another case? So first of all, both questions are using what's called interval notation. And in interval notation, you have a lower bound number, you have an upper bound number, and you're going to use either parentheses or brackets next to the lower bound number, or parentheses or brackets next to the upper bound number. And when we look at this notation, this is describing all of the numbers between the lower bound and the upper bound. So it's not just an individual ordered pair. It's not an ordered pair at all. It is an interval of numbers, which is why it's called interval notation. It's an interval of numbers that starts here and ends here. And these parentheses and brackets that we put on the end are supposed to tell us whether we include the numbers on the end or don't include the numbers on the end. So the parentheses mean that we do not include, and the brackets mean that we do include those lower bound and upper bound. Okay, so that's first part, making sure we understand what the parentheses and the brackets mean. Now, with the, I've put in some definitions from our notes. Definition of domain. Domain is the set of all first coordinates, which is our x's. And over here, I've also put in the definition of increasing. Now, what I want to emphasize here is that different sources will define increasing in different ways. Domain is pretty solid across all sources of being first coordinates and the x's, but the definition of increasing, very slightly different wordings, different technical things can change the way that we answer this question. Not hugely, but slightly. So the definition that I'm using right now is from my college algebra class. And this is the definition that's given. A function f is increasing on the interval a to b. So I wanted to point this part out here because in the definition, they are using interval notation and they're using the parentheses here. So in the definition, we are not using the endpoints. We're only using the interval itself in between a and b. So let me continue. A function f is increasing on an interval from a to b if for any x sub 1 and x sub 2 chosen from the interval, with x sub 1 being less than x sub 2, then f of x sub 1 is less than f of x sub 2. So in a little bit less technical terms, the graph of an increasing function always goes up from left to right. So our y's on the right will be larger than our y's on the left. So just going back to the reason why we're using parentheses when we're talking about increasing, decreasing, and constant. We're using parentheses because that is how the definition has been stated to us. There are other textbooks. In fact, my pre-calculus textbook words the definition in a way that does allow for there to be brackets on your interval, and you would answer sometimes the question with brackets in that class. So I know that's not the best answer to say sometimes we use brackets, sometimes we don't. But in this class, because the definition is worded in this way, where we use parentheses on our interval, all of the answers will use parentheses for increasing, decreasing, and constant. So while we have these questions up here, let me just explain how I would come about answering them, even though we already have the answers written right here. So in this first question, we are going to use this graph to determine the domain and range of the function. And maybe I can even zoom in on this a little bit. So if I'm looking for the domain and range of a function, I'm going to use a pencil or a ruler, and I'm going to hold that ruler vertically to find the domain and horizontally to find the range. So when I hold it vertically, I am pointing to the x scale. So I'm thinking of this as a line, and this line points to somewhere on the x scale. So it's going to help me identify where the x's start and the x's stop. Remember that domain is the set of all x's. So I can see here that the first time my vertical line, my ruler, my pencil is hitting the graph is right here at this point. This point is 3, 7. So that is when my domain is going to start. I'm going to keep moving my pencil from left to right. I always go from left to right because interval notation goes smallest to largest, and left to right is smallest to largest on our x-axis. So I keep moving, and I notice that all this time that I'm moving, I'm touching the graph. Every time I touch the graph, I have an x value that's part of the domain. So all of this is part of the domain. And it's not until I get to here, this last point, is when my domain stops. So I know my domain stops right here. So now I have an interval of numbers from -3 to 6. I'm using the x coordinates. The interval of numbers are all of the x's on this graph, and my domain goes from -3 to 6. I used brackets because these points on the end are included. So then I'm going to find the range. To find the range, I'm going to hold my ruler horizontally. And I'm holding it horizontally because that's going to mark out the y-axis. The range is the y-axis, the y values, the y coordinates. So I start from bottom to top. Interval notation goes smallest to largest, and going from bottom to top is going to give me the smaller number first. So this right here is the first time I'm hitting the graph. So this is where my range will start. If I continue up, I'm touching the graph. Every time I'm touching the graph, I have a y coordinate that is part of the range. I continue to go up, And this is the last point that I'm touching, and this is where my range will stop. So that range value is the y value, that's 0 to 7. So my range is going to go from 0 to 7. And once again, these points are closed circles. They're on the graph. So I'm going to include those points in the range. Okay, so I've shifted over here to the other picture, and I'm going to erase some of this so it's not quite as messy. And on this one, we want to determine the intervals of increasing, decreasing, and constant. So first I want to get an overall idea from the picture. And from this picture, we're going to start on the left and move to the right. And the reason why we do that is in the definition of increasing and decreasing over here. We want x1 to be less than x2. We want to start on the small side and work to the bigger side. So we're going to go from left to right. And the increasing and decreasing refers to what is happening with the y values. F of x1 and f of x2 are the y values. So as we go from left to right, we're going to observe what is happening to the y. So starting from here and moving this way, our y values are decreasing, then increasing, then decreasing, then constant. So I'm going to label that with some colors. Let's do decreasing as red. We'll do increasing as purple and constant as green. So we're able to identify the decreasing, the increasing, and the constant, but we've got to be able to write the answer down the way that we're being asked over here. So the function is increasing on the interval. We're going to use interval notation separated by commas. And what we need to know is that what we write down here, what they're asking us for are intervals of x's. Maybe I shouldn't write that in green. Intervals of x's. So when I look at this picture, what I'm looking at is when does this interval start and stop on the x scale. So this first one that we see here goes from -5 to 0. And that's decreasing, but then we have another decreasing that starts at 3 and goes to 7. So that's what you see right here in the decreasing answer, -5 to 0, using parentheses, 3 to 7, using parentheses, and the answer separated by a comma. And then if we look at our increasing interval, we have that one in purple. It starts at 0 and goes to 3, and that's what you see here in your answer, using parentheses. And then we have our constant interval. This constant interval starts at 7. The arrow means it's going on forever, so our upper bound is infinity. So right here we have 7 to infinity using parentheses. On this question, we want to use the graph of y equals f of x to answer the question. On what intervals is f increasing, decreasing, or constant? So when we look at this picture, we see this graph in red, which is labeled up here as y equals f of x. And when I'm looking for the intervals of increasing, decreasing, and constant, what I'm going to do is try to look at the picture overall to start with. And what I do is I trace the graph going from left to right. And the reason why I do that is because in the definitions of increasing, decreasing, and constant, all of those definitions describe x sub 1 being less than x sub 2. So that's telling us to go from the smaller to the larger value. And so on the x-axis, the smaller values lie on the left. So I'm going to start on the left. And as I trace over this graph, what I'm going to pay attention to is the y values. These words of increasing, decreasing, and constant, these are words that are describing the y. So as I go trace through this graph, I can see that along this path, the y's are constant, they're not changing. So all of these y values are 4. Then the y values are decreasing along this section, increasing along this section, decreasing along this section, then increasing, then decreasing, then increasing, and then constant. So I want to label all of these intervals, and I'll do that with some different colors. So we said that this section and this section of the graph are constant. Then this section is decreasing. This section is decreasing. And this section is decreasing. And then we have some sections that are increasing. And so we can visually see on the graph where these different sections are increasing, decreasing, and constant. And when we write down, when we try to answer the question on what intervals, this question is asking us to state the x's, the intervals of x, where the increasing, decreasing, and constant are occurring. So when I look at those x intervals, I'm imagining this line being sort of projected down onto the x-axis, and where is that interval starting and stopping. So because of this arrow, it's starting at negative infinity and stopping at an x of negative 6. So we have an interval of constant which goes from negative infinity to negative 6. Now, I've used open intervals because the definition in this book gives open intervals, but there are other definitions, other sources where the definition could include closed intervals as well. And a closed interval would be if you had a bracket on this negative 6 instead of a parenthesis. But this book uses open intervals. So we also have a constant interval that is over here that starts at 6, and because of this arrow goes on forever to infinity. So we have the intervals of constant being from negative infinity to negative 6, union with 6 to infinity. So then let's write down the intervals of increasing. And those are the blue intervals that you see. And remember, we're going to be writing down the intervals of x. So this interval of x starts at negative 5 and goes to negative 4. And then we have an interval of x which starts at 0 and goes to 4. And remember, this book uses open intervals, which is why I'm using parentheses on this. And then we have some intervals of decreasing. Those are in this kind of pink color. This interval will start at -6 and stop at -5. We have another one which starts at -4 and stops at 0. And we have another one which starts at 4 and continues on to 5. And I apologize, I've just noticed that I left off an increasing interval. So you can see this little section right here I left off. So there's one more increasing interval which starts at 5 and stops at 6. So if you're going to be answering this question in my math lab, pay attention to the blue writing next to the blank because I believe it says to separate the intervals by commas. So you may be using, instead of the union symbol here, a comma between these intervals. So as our final answer, we have intervals of constant being from -infinity to -6, union with 6 to infinity. Intervals of increasing being from -5 to -4, 0 to 4, and 5 to 6. And intervals of decreasing from -6 to -5, -4 to 0, and 4 to 5. Thank you for checking out my videos. Have a great day.